time theory of architecture. I think I know why I'm here, which is that this is supposed to be multidisciplinary. And so if you get me, you get these areas. And I will get as far as I can. Okay, so a recent paper has an attempt to talk about some of this in a way that is really for quite a broad but engineering audience. And that's a very bizarre transactions. I mean, systems man and cybernetics, like weird. Very 50s. So I'm interested in robustness and fragility in complex networks. So I'm going to try to be concrete about what I mean here for a minute. So on the right here, we see a bunch of fragilities that we currently have epidemics of. And one of the things we can ask is, what are the mechanisms responsible for these? And you all know, fat accumulation, insulin resistance, uncontrolled cell proliferation, and inflammation. Inflammation is actually involved in all of it. But we can also ask, are there corresponding robust systems that we have? And we have an incredible metabolism. We have the ability to regenerate and repair mildly damaged tissue, and we can heal wounds and infections. So if you think of what we were like between, say, 1 million and 200,000 years ago when all of our ancestors lived near the equator in Africa, we had some really kick-ass capabilities. We can run down a horse at the equator. Well, at least some of us can. At least Paul can. Or whatever. Okay. And now you can ask, what are the mechanisms? What are the mechanisms that make this so robust? Fat accumulation when you can, insulin resistance to preserve glucose for the brain, cell proliferation, and inflammation. So inflammation is the most important player in all of this, on both sides. So what's the difference? Well, the difference is this is in a fluctuating energy environment, and this is in a static one, more or less. I mean, it's somewhat oversimplification. A little more is that on the left side is controlled and dynamic, and on the right side it's uncontrolled and chronic. So think about the brakes in your car. Your brakes in your car should be used occasionally. If they're ever on all the time, something's probably wrong. And so if we want to fix this, we've got to go from this uncontrolled, chronic, high mean, very low variability state of these things to being low mean on occasionally, okay? And so there's these common mechanisms. And if we want to understand, this doesn't even have the control. This is not the information part of it. This is just the metabolites. This is the simple part that we would need to understand to fix this problem. Let's go on. We have a complex neuroendocrine system that sits on top of all of this and run things, but in a modern environment we have addiction and psychosis. We create complex societies. We have epidemics, war, monotheism, masculinity, all of these problems. Which may in some sense be the only problem. We have all these advanced technologies, and then we have disasters and global. But I should say at the outset that I am actually a global warming. I'm a skeptic. I think the models are wrong. I think it's way worse than they're telling us.
You're both way more interesting.
So.
The bullet symbols.
Yeah. So we have risk management, right, which turns out to be to obfuscate and amplify. And the question is this an accident or necessity? And the idea is that these fragilities are all actually not independent of the robustness processes. The mechanisms are the same. It's the same mechanism, but they've been hijacked, or there's a side effect, or there's some unintended consequences of the mechanisms. And the mechanisms really evolved originally to provide some specific robustness, which has now been lost. And so the complexity in all these situations is really to control this spiral of robustness and fragility. And what I'm going to talk about a little bit is that there actually are conservation laws. And I don't like the word law, but if you did not understand that, say, carbon was conserved, you would be confused both about metabolism and about things like global warming. And apparently some people are confused. But things like energy is conserved, small moieties, that is, carbon atoms, are conserved in most of the processes that we can operate. And the idea is that robustness and fragility are in some sense conserved, that I want to talk about a little bit. And the question is accident or necessity? Well, it's both. It's necessary that there's trade-offs. So it's necessary that carbon is conserved. It's necessary that energy is conserved. It's not necessary that we create global warming, perhaps. And so it's an accident that it's played out the way it has, but it's necessary that the trade-offs that force that play out are there and unavoidable. So we have to figure out what's unavoidable, what can we not get around, we just have to face up to, and then what can we fix. And we have a surprisingly murky understanding of that. And so how does architecture come in? These essentially are all the same thing. They're all the consequences of modern architectures coming into contact with ancient ones, either ecosystems or physiology. And how do we fix that? So, of course, most people don't think this is a problem, right? You know, don't worry. Whatever your particular religion is, you don't worry about these things. My favorite, of course, is like, dude, like, chill. The problem is, this is sort of the bad news. This is all because we live in this virtual world where we don't worry about where our waste goes, we don't worry where our food comes, we don't have to exercise, we don't have to do anything. And so even though we think of virtual worlds as being inside computers, in fact, we sort of live in a highly virtualized world right now. That's why I was saying this talk would be better if you were hungry and the room is still too hot and thirsty and maybe a little bit sick. The problem is, in dealing with this, the only thing that matters is the actions we take. Everything we do up to that point doesn't matter. It's only preparing us to take actions. And I think we forget about that sometimes. But the reason I'm here is that we need we're already down the road of networks and automation, and we have to go further. We have to automate maybe everything. We maybe have to build the matrix, because that's the only way we can make humans sustainable on this planet. What I want to talk about is with limits and trade-offs. So the problem is, we want to stop building systems that are fragile and wasteful, right? And then the question is, what frameworks do we have to start thinking about that in a more systematic way? So the problem is, we seem to be able to build some systems that are robust and extremely wasteful in every possible way you can think of. And then you can build systems that are apparently more efficient, but are much more fragile, again, in many different ways. Is that because we have bad theories, we have bad architectures? What's the gap between them? Well, we have a lot of deep theories, right, in these areas, but they're fragmented and they're incoherent and they don't fit together very well. And they're also not very complete. And the problem is each sort of focuses on one dimension of the problem, but all the hard trade-offs are between dimensions. And some progress, so that's what I want to talk about. So how could we approach this problem? There's a few things we could do. We could try to figure out what the hard limits are. So we know there's hard limits on how efficient we can be, that we can't be more than 100% efficient, and if someone shows us a perpetual motion machine, we're pretty confident there's a flaw and we go look for it, right? It turns out there's similar things for fragility, there's balance in that, but there's an interplay between them, and presumably, but there's no theory that tells us that's the case. We also want to try to find case studies that are close to the theory, okay? And the ones that are any good or any interesting are all in biology. And that's a hard problem. And then the easiest thing to do in some sense is just find and fix bugs. I mean, most of our systems are so far from any hard limits. It's like when our steam engines were 0.1% efficient, you didn't need to know what 100% was. You were happy to get to 2%. And we're kind of that with respect to the infrastructure we have with respect to these issues. So we can do a lot of bug fixing. And we can do that without really knowing where this is. And I think if you can even get people interested in trying to do this problem without worrying about this deeper theory of what are the ultimate limits, then I think that's still useful. So I'm going to do a little case study just to talk about what would this look like. And unfortunately, I'm going to tell you a cartoon version of the story. The reason it's a long-standing mystery. It depends on whether you depends on who you count, centuries or millennia. The components, every part of the story I'm going to tell you is absolutely well known to somebody. It's just putting it together is the issue. It combines a bunch of different things. It's broadly relevant. It turns out it's in every cell on the planet. And there's a science paper that should appear in the next week or two. Hopefully you'll read it and get some of the details. And the response to this is extreme. So you get reviews, NIH reviews that are 1s and 9s. So either the best thing I've seen in 25 years of reviewing for NIH, or if this stuff is allowed to be funded, the civilization as we know it will end. and nothing in between. So, okay, so here's the issue. Why are there glycolytic oscillations? And it amounts to a trade-off. This is the most studied circuit in all of science or engineering. Like I said, it's in every cell. There's 10 to the 30th cells on the planet, and it's in every one. And what we can do is we can actually prove some hard limits. And between metabolic overhead and the fragility network in terms of disturbance rejection. And so we can make all this stuff precise. And here's a typical experiment. What this is I'm not going to tell you the details, but it's been studied to death for forever. And so it's known that you can create circumstances under which cells will go into spontaneous oscillation. And there's diseases associated with this. We're going to worry about it in yeast because yeast is the easiest thing to work with. And this is a standard simulation. So there's we try to avoid any innovation whatsoever in the parts. So for decades, people have been able to run simulations and reproduce the behavior. So it's not like we don't know, in some sense, how it works. The question is why. And there's always a proximal answer. Oh, phosphofructokinase is blah, 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 right? There's a proximal answer. But there's a deeper answer, which is why would evolution evolve a system that had this particular fragility? And like I said, it is a disease state in humans. And so it turns out there's a theorem that says it's really a hard trade-off. Now the problem with this is to flesh this out would take more than even if I had the rest of the afternoon, unless you knew a lot of biochemistry. So it turns out there's a well-known, like again, standard analogous system that I can show you the same trade-offs in. Now it's kind of boring because the x-axis is not anything having to do with efficiency, but so this is a classic undergraduate thing we teach to everybody. So pendulum, it's not pendulum on a cart. I'm in an inverted pendulum, and so I'm going to balance this thing. And it turns out it has mathematically the same issue that this glycolysis case has, which is, now it turns out actually the glycolysis case is easier to understand than this if you know some biochemistry, but I'm assuming you don't, so you can visualize this pretty easily. So I'm trying to balance this thing. Okay. So what are the issues? I want to balance it. Oh, so how does it relate? Well, here's a sort of a minimal diagram of this system. It's a cartoon. These are metabolites, these are reactions. The blue and purple lines are flows of metabolites through reactions. The reds are control feedbacks, and I haven't put them all in because you wouldn't be able to see anything. There's a lot more feedback in these systems than there is anything else. And this is not a graph, it's a cartoon, and you can't turn it into a graph and make it preserve anything meaningful. What you want to do is there's a differential equation here, and you want to write down the differential equation, and then you simulate it, and you do reproduce the behavior that you see in the experiments. And again, the question's why. So it turns out, mathematically, the autocatalytic loop of ATP is like being in the up position. And then we'll see that having complex versus simple enzymes, and biology chooses to take great complexity in this network. It has apparently gratuitous complexity, and it turns out that mathematically that's equivalent to having your eyes open or closed and trying to stabilize that. So I'm not going to talk about this anymore. I'm just going to talk about the pendulum. And hopefully you'll read the paper, which actually it's intended to be really accessible and simple. We took all the math out, and they said it had too much math, which was okay. But they've never published anything like this before, so they really worked with us to try to get it something that would be accessible. So it turns out, let me just do this. So the idea is that as I shorten this, it gets impossible, right? As I shorten it, it becomes impossible to do. Shorten enough, and it's just completely hopeless, right? Whereas in the down, I put this on top so it's easy to visualize. It also helps a little bit. Down is easy, okay? Right? I can do down with my eyes closed, right? Okay. And there's a theorem that says exactly why, and it's really easy. And again, this is standard undergraduate stuff, and you can play with it and try it, okay? And so you can get a trade-off between the length and the fragility in a quantitative way that says no matter what you do, no matter how good you are, eventually it'll be impossible, okay? And easy down. And it's a simple theorem. It's called Bode's integral formula, kind of standard undergraduate control thing. Now the problem is, the same theorem applies to eyes closed, which is completely impossible. And in principle, again, if you're taking a class in control, it's controllable and observable, so in principle I should be able to stabilize. But I can't because it's simply too fragile, and there's almost no way to, there's just simply no way to do it. And so what happens is this curve is like this. So the idea is that up with no eyes is so fragile that no matter what I do, it's hopeless. As I add pretty enormous complexity, I add vision. Our vision system is extremely complex. I get this, and then down is easier still. So it turns out that maps directly onto this picture. Turns out simple enzymes look like this, complex enzymes look like this. And then you ask, what's the purpose of the oscillation? There's no purpose. Notice that my hand oscillates in trying to control this a little bit. That's just an outcome of the control system. There's no function to that. It's a side effect. It's simply a side effect. And that's, we believe, the same case here. So now you have to do a bunch of experiments, blah, 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 of course. And, but this is simply also, people had not realized why does biology use this apparent gratuitous complexity? It seems more complex than it needs to be. It's got all sorts of extra loops. Is it redundant? No, it isn't. It actually is there for a real reason. But you still get oscillations. So now the architecture issue comes up because it has a very specific architecture here, and it's necessary to have that architecture in order to get on this curve of fairly robust control. And then you see this little ringiness. So it turns out there's been, and again, I'm not going to go through all this, it's in the paper. There's all these mysteries about the experiments and this and that, and this doesn't clear them all up, but it clears a lot of them up. Why does it oscillate in these conditions and not in these others? So it really cleared up a lot of stuff, but as anything, you create more questions than you answer with this sort of study, and I hope we've done that as well. Let me just say one thing about this. This axis is general, rigorous, and first principles. In fact, this axis is not. We're taking a phenomenological description of enzyme complexity and efficiency. I don't doubt that the biochemists are right when they tell us these stories about it, but you'd like to say, well, what does that depend on? Well, it depends on thermodynamics and stat mech, and you'd go to that, and it turns out that's completely useless for this kind of problem because it's far from equilibrium. And so we really need to connect this with this. And we're starting to do that. So we're trying to basically redoing statistical mechanics from scratch. Here's a paper if you're interested in. So there's another issue, which is a big place of inefficiency turns out to show up in turbulent drag. And so drag over streamlined vehicles remains a mystery, again, for the last century. So we're starting to sort out why that is, again, using sort of similar mathematics. But I want to talk a little bit about this finding and fixing bugs part. So I want to say a little bit about layered architectures. It turns out the best case studies in layered architectures come from biology, but we have a few examples of our own. So let's just think about the usual one with TCP/IP in the middle. And there's sort of this mathematical theory, which is, again, a mathematical theory of network architectures, rather overstated. But I couldn't think of a better one, and I wasn't the main author on this. So even as pretentious a title as my talk. But as an attempt, actually, this is, over the last decade, has really developed a theory for the existing internet. And so the idea is that we've had really 10 years of progress. We started out with static optimization problems. Now we really have dynamic control, wireless scheduling, network coding. It's really built into a very nice theory. But there's really something fundamentally wrong architecturally. And tweaking these protocols, tweaking the algorithms without changing the architecture isn't going to get us very far. And it turns out layered architectures are everywhere, and we can learn from them. So let me just run through something very quickly. So I'm going to say something that, if you're a networking person, is utterly trivial or completely full of shit, depending on who you are. And nobody in between, right? So we had one battle, which was sort of this pathway view versus the layered view, and the operating system crowd won out, and they're really responsible for the architecture we now have. And it's a great one, right? But let's think about this from an OS point of view. What does an operating system do? Well, it allocates and shares diverse resources among diverse applications, but you must maintain strict layering. You want to have an application namespace, you want a virtual name and address space, and then you want a physical name and address space. And so then you do name resolution within applications and name address translation across layers. So, but basically, we all learned, when we were in high school, no global variables, and when we got to college, we found out you don't cross layers in the operating system. Absolutely don't, right? And you certainly don't give applications direct access to physical memory, because then you'd have applications crashing your laptop, which of course never happens, right? So the problems with this leaky labeling is, okay, so you have global variables, you have poor portability, you have insecurity of the physical address space, your fragile applications, you have no scalability of the if you don't have a virtual addressing space, you have no scalability. Now my real reason is that the current architecture limits what we can do with this math framework. So honestly, I have this hidden agenda. I want to do more math, and the current architecture is broken with respect to math, but there are other reasons, right? So let's go back to this and say, what does an IP address? It addresses interfaces, not nodes. Okay, you know that. But what does DNS do? It gives you global and direct access to physical addresses across the network. This is insane. You lose all the features. It's exactly what we learned not to do when we, in our first course, right? And so what's wrong with this? You got a global address space. So what's the worst thing you could do is make it bigger, right? Which is what IPv6 does. So you get all these problems, like, why do you have NATs? Well, NATs are trying to carve out local address space, which is what we should have in the first place. So why do we have firewalls and all that kind of stuff? So this is a nightmare in the current IP. So all these problems you can sort of translate. Just an aside, architecture is not graph topology. What's the graph of the internet? Well, it depends on which layer you look in. They're all different. And the whole point is a good architecture supports arbitrary things, right? So this has been a persistent source of errors and confusion. So the big problem, though, is that we need to layer things in another dimension when we do cyber physical. We don't know how to do this very well. Some later today is going to be talking about real time, so I'm not going to talk about that. Crucial issue. We've got to get our heads together about doing real-time control over networks. Doing real-time control over IP is a nightmare. It's a disaster. So you think security is bad? Wait till you try to do real time. So let me give you a little idea about your layered architecture. So it turns out we have one kind of layering, which is we have cells, organs, and physiology, and cells inside are layered. But our cortex is also layered. And it has an interesting feature, which is if you think about, say, vision, there's 10 times as many wires going out towards the eye as going in towards the brain. It's this picture. So what you do is you predict actions, and you predict what you expect to see, and you get back errors. That's why you dream so vividly. But it has side effects. It has consequences. So which blue line is longer? Okay, well, obviously this one is. Okay. Now which blue line is longer? Now which blue line is longer? Right? So this is called a visual illusion. And the question is, why are you getting it wrong here? Why do you see the right one as longer when they're the same length? Well, the reason is you're not wrong. You've evolved for millions of years to immediately infer 3D dimensions and 2D plus. There's no selective pressure for you to be able to tell on a PowerPoint slide whether or not those two lines are the same. Right? So everything you're good at is reflex and automated. And when you get good at something, it becomes unconscious. And the part of our brain that is conscious and reasoning is so trivial and tiny, we don't really do much with it. The more interesting, so this is an unavoidable consequence of a layered architecture. Now, if we understand it, we don't get confused by it. But we get confused constantly because our brains do all sorts of things, and we make all sorts of decisions that are really stupid. And so it's the interaction with that. So that whole long list of problems on the right-hand side that I started out with are all due to things like this. The more interesting question is this question, which is which blue line is longer? And so there's been extensive studies done which show that if you get confederates to first say this one's longer, we go around the room, and then the fifth person will say like 80% of the time that this one's longer. And what's interesting is you do fMRI studies, and they see it as longer. It's not that you see this one is longer and go, I don't want to. So it's not that you might go. Here's what happens: is people see this, they go, oh, it's longer, but gosh, what am I missing? Or this must be a joke. I'm just going to go along with everybody. I'm going to say left one. No, you actually see the left one is longer. This has been studied to death, right? And this is a consequence of architecture. So these things have consequences, and there's reasons why we're that way, actually. Very good reasons. So again, 1,000,000 years ago, a great way to be. Right now, we need to balance this. We need to balance this wanting to go along, wanting to get along, with wanting to embrace our diversity and get a diversity of opinions. Okay, so what we have is we have this architecture that takes very fast and limited scope at the periphery, distributed, and then we have this slow broad scope, and we blend those together to make a pretty amazing computational device, completely unlike computers, but it does have a layered architecture. We can learn a lot from that layered architecture, and neuroscientists can learn a lot from what we know about layering. So again, what's the fix here is we really need to do all these things, and like I said, they're sort of all the same problem in some sense. They look very different, but they all have to do with these side effects of architectures, but on different scales. So a few things that I think aren't going to help, and this is one of the things that's not going to help. It's not true that we have enough data, we don't need theory. I love this end of theory. Of course, no one here believes this. So I've decided I want to start a new program, Save Our Children, okay? Stop pedophilia. And there's a treatment. It's not normally used. So there's a whole bunch of these other words. Pedophilia is a perverse love of data in large competition. Of course, I know I shouldn't be saying that in this crowd, but I think we have to be cautious about some of these things. So there seems to be a treatment. It's not yet in widespread use, but it's called CLU, and you can get injections from your friends, in fact. But you have to actually filter them a bit. So this is a picture. I think I very, very, 30,000 foot flyover. But we live out here. We've got to get down here. We don't even know where this is. We can do a lot by just heading there, right? We can just fix bugs. And there's stuff that's so wrong with what we do now that we just need to fix bugs. But there's a general program here which I think we need to sort of at least all of us be aware of and thinking about, in that it's really these dimensions, and I've just put two up here, fragility and waste, where we're extremely fragile, extremely wasteful. We've got to get better on both. And so that's kind of the picture I'm trying to, and the idea is that we're calling these laws, because they're conservation laws, bad word. They're really just constraints that come out that are they're mathematical constraints, like conservation of energy is. Well, that's a physics constraint, but you can think of it mathematically. So I don't know what to call them quite. But then we need to think about architecture and getting down to this other side. So stop. Questions? And by the way, we can make things worse, but yeah.
So I loved it when you said that there's fluctuations are a side effect, not an actual designed-in characteristic.
Right. Unavoidable side effect of something else that was selected for.
Right, exactly. So paleontologists Stephen Jay Gould and Richard Lewis have a word for this called spandrels.
No, it's not spandrels.
Not spandrels?
No, it absolutely is not.
Well, okay, so let's just talk about things that are not designed in, but which are nonetheless appear.
That can be, yeah. A spandrel is an entirely,
Okay, well,
there are
that's fine.
spandrels.
That's fine, let's not worry about it.
Okay, I can give you a million examples of spandrels. This is not an
We'll talk
example.
later. But my question
Yeah.
is, if we've got these things that are side effects, sometimes they are really deeply embedded.
Yep. This one is.
How do we deal with that kind of design constraint when we've got this deep embedding?
So I think that most of the problems over here do not involve this kind of deeply embedded side effect. Okay. I'm asserting that.
That would be convenient.
And so, for example, I think we can make substantial progress in curing metabolic syndrome, diabetes, obesity, cancer, autoinflammatory autoimmune diseases. I think we can make substantial progress on all of them way before we'll make any progress on them individually. And because there are deep underlying mechanisms that they have in common, they are interactions between us and our environment. I think we can fix those before we understand in detail how they all play out. Once things are broken, how does the cascading failure happen? I think stopping the break much earlier on is very doable, and we'll never fix, it'll be decades before we cure cancer in the way we're thinking about curing it now. So I think there's some hope. I mean, I think we're far from the hard limits in most of the things we're doing. So in some sense, even doing research on the research I just showed you about glycolysis, that's maybe a boutique area, because we're not going to be running up against that many of those kinds of situations. We're up against hard limits. But then we'll take offline why this isn't a spandrel. But that's actually a very good question, because these things that are truly accidental, as opposed to side effects of hard trade-offs, are very different things. And so that's something we should talk about. I think we're in the accidental crap, buggy stuff big time. So.
Should we thank the speaker? Thank you.